the Anaconda Navigator. And today we're going to use Spider. Okay, so you just go to Spider and you click launch. Okay, so once that is launched, you will see this screen, right? So this is Spider, which is like the Python implementation of MATLAB, as I said in the last time. And just to repeat again what you're looking at, so we have on the left side the scripting environment. On the right side, you have the variable, explorer, and plots. And here you have the console. Okay, so this is where we were typing like 1 + 1 gives you immediately the output. Whereas in the script, if I type 1 + 1 and I hit enter, nothing happens because you have to press run, okay, or F5, or I think on Mac there's also shift enter. Okay, that just runs one line. But basically you can just hit this green run button and it will run your script. And as you see, there's no output because simple internal calculations are not stored as an output, which is unlike the command line, right? So if I want to see what is going on, I can, for example, say A equals 1 + 1. And if I run this, then as an output, I have now a variable, right, that is called A, which is in this case an integer. There's only one integer in A and the value is 2. Okay, so let's get started with something simple. So in the comment field here between these green triple quote signs, we can type some description of your script. So you can type something like, this is my first script. Okay, and we're going to solve an equation, and that is y equals 2 times x squared. Okay, I'm going to delete this. So let's get started. We need a number of aspects that we have to consider. So we're going to use a number of packages, libraries that we need to import. Okay, so the first one is NumPy. I already introduced it briefly last time. So we're going to say import. It will turn blue. NumPy as NP. Okay. So not sure if in your version, when you start typing, there's this kind of autocomplete. There's a little nice plugin that is called Kite that you can download. It interfaces and it makes suggestions for your code, but you don't really need that. So let's continue like this. And we're going to use matplotlib. So we're going to do import matplotlib .pyplot as plt. And you see that in the little thing that folds out, it says provides a MATLAB-like plotting framework. So you'll see that if you have used MATLAB or you will use MATLAB in the future, that it's really quite similar. The plotting capabilities, the solving capabilities. So anyway, that's just if you want to switch between those two packages. Okay, so we have imported. If you want to put a comment, use the pound sign. So you can say importing libraries. This is just a good habit to keep your code as clean as possible by using comments. So I'm going to say first, define, let me just keep it simple, the values of the x-axis. Okay, so the first thing I'm going to use is I'm going to say x equals np. So np is numpy, right? So we are naming the numpy library as np. So I'm saying np dot linspace, which is a linear distribution of numbers, right, with a certain starting value, a stopping value, and a number of values. And I'm going to say 0, 10, 101. So that means I'm going to start at 0, I'm going to count to 10, and I'm going to do that with 101 points. Okay. If you want to see what a certain line does, you can, for example, copy this, Control-C, Control-V, to the console. And if you run it there, okay, here it says name np is not defined, because in the console, actually, I didn't import the libraries because I didn't run this script yet. So this has not been imported. Or I can just run the script here. And now you see that it said I ran the file in this directory and everything was fine. And you see a variable x, which is an array of float 64, so numbers with high accuracy behind the comma. And I have 101 values in my array x. And these are the values. Again, if you double click on this, you will expand all the values. Okay, so that's that. And I'm going to show you 3 different styles of solving the same equation. Okay, the first one. So what I'm going to do is I'm going to pre-allocate a result array. Okay, what does that mean? I'm just going to make something that I'm going to call y out 1 and y out 2. So what am I doing? I'm just making a variable which is initially empty, and I'm going to append what we saw in the previous class. I'm going to use the append function to add values at the back of that. Okay. So let me call this Python style. And I'm going to use a for loop. What is it? Using a for loop. Okay. So I have my array of x values, and I want to solve in my equation. I want to know for each value of x, what is the value of y? Okay. How do we do that? I'm going to use a for loop. I say for number in x. So this means I'm going for each value in the array of x, I'm going to run this loop, and I'm going to assign, the first value, so index 0, which is 0, to a variable that I call number. And now I can use this number in my calculation. So I'm going to make a temporary value. You'll see why. So I call it y temporary is 2 times number squared. So 2 asterisks is to the power, right? So this is 2 times the number squared. And I'm going to do y out, y underscore out 1 dot append y temp. Okay. So that's my for loop. So again, to run you through, so x we make as an array with 101 values going from 0 to 10. In this for loop, I say, okay, how many numbers are there in x, or 101? Take the first number that I can call whatever I want and calculate that one y value, append it to my empty y out 1, then go back and do the same thing for number 2 in x, run this loop. So y temp will be overwritten by the next loop. You calculate again y temp and append it. Okay, let's see what it looks like. So we run this whole script and we see we have now y temp, which is 200. Why? Because it will show the last value that it used in the for loop. So the last value of x is 10, right? 2 times 10 squared is 200. So y temp is stuck at the last value of my for loop, which is 200. And y out 1 is a list, which has also 101 numbers. And these are the y values that correspond to these x values, right? So the last one will be 200. We can check that. If we say y out 1 bracket minus 1. So this is the Python way of saying, give me the last value of the array y out 1. That's 200, right? So this seems to be right. Okay, so that's a very, well, nice way to do this first calculation. There is another way we could do it, that is using calculate directly using the array. Okay, the array x, let's say. So make sure you pay attention to the indentation of your code, right? So it's not the same if you write something at this level or really all the way to the left. So be careful with that. Of course, the simplest way I could have done it is just say, let's call it y simple is 2 times x squared. Only need one line, right? So Python in NumPy, it supports matrix calculations. So I can directly take the entire vector or array x, and if I do squared, it will take each value of the vector x and square it and calculate y simple. So let's run this whole script. Okay, so I see basically the same. I have an array, 101 numbers, and it should have the same values as y out 1. The small difference is that y out 1 is a list and y simple is an array of float. Okay, but we don't really care about that at the moment. Okay, last and third method. Let's say calculate by making a function or defined function. So last class, I showed you how to make your own function. So we can say, okay, define def an equation that I'm going to call EQ. And as an input, it has X, colon, very important. And then I'm going to say, so I pressed tab. I was here at the same level. I pressed tab and I say return 2 times x squared. So when I run this, it doesn't actually give any output because I'm just defining the function. But let's see how that goes. Okay, so now we come to the part where we're going to make some plots, and we hope that we can see if there's any difference between those three methods, right? So I'm going to say make plot, okay, plots. Well, I'm going to make one plot. And the first thing I'm going to do is plt dot figure. So it's going to create a new figure. And so plt is here, right? So that was matplotlib.pyplot, and we renamed it as plt. Okay, so we can do plt.plot x comma y underscore out 1, and then I do O between single parentheses. Okay, so this is going to plot the results of the Python style. Okay, I'm going to plot another line. So this will, the first line, so line 34, will make the figure, and the second line will fill the figure with that data, and it's going to use these scatter plot with symbols. You'll see. Maybe we can just run this and see what it looks like. So I press run. Okay, there's an error. Y has no attribute plt. Why not?
There is no mistake. I've got the figure.
Sorry?
For me, the figure appear.
Okay. Yeah, it's weird.
It's plot, not PLT. PLT.plot.
Oh, right. There you go. Thank you. Yeah, typos are annoying. There you go. Right. So we see a figure, and we have this 101 data points, and they are, let's say, closed symbols, and it takes just the default color. Okay, so let's add the other results and see what that looks like. Okay, let's delete this. And I'm going to say plt.plot this time. And I'm going to say x comma y underscore simple s, for example. So that will plot the results of, method 2, which is the direct calculation. So that's for this one where I called y simple is 2 times x squared. Okay, let's hit again play. We run the file, and okay, now you don't see because we have squares, orange squares, that is blocking the other one, but you can see that the two lines are exactly on top of each other. And let's add the third one, so we can do plt.plot x, and I just type equation x, and I'm going to do minus b. Let's plot using method 3 defined version.
Sorry to
Okay.
interrupt, but what is the point of O, S, and B, and minus B?
Yeah, so O it's the type of symbol. So this is open, like circles. This is squares, and this is a line. It's
Oh,
this,
okay.
you can choose the style. So you see now you have, it's a bit hard to see the blue square, the blue circles below, but they're okay. If I zoom in or out, okay, it's not really great. Okay, so the minus, let's say this means a line, and B is black. So I have a black line, and I have orange squares and open circles. So you can choose. I don't know all the abbreviations. I usually just try out. So I think if you do double minus here, it will be a dashed line. See? So you can choose the style. If you go to the Matplotlib just online, it will give you all the overview of all the different types of things that you can use in your plot.
Okay, thank you.
Yeah, no problem. So one last thing which is useful, of course, is to add labels. So you can do plt.x label, and then you can say, for example, we call the x-axis x, and plt.y label y. Okay, so if we run everything, now we have a plot that has an x-axis with label x and a y-axis with label y. So you can make your plot, and then if you're happy with your plot, you can save it as PNG or whatever you want. Let's just save it wherever. And then you have your figure saved. Okay, so what's interesting maybe is that in this line, we're actually doing the calculation of the function not before, but directly in the plot function. So only when the code comes to this line and it sees equation x, it calculates directly the result and puts it into the plot. So that's just different ways of understanding how that works. Okay, that was the very, very basic plot. Maybe an interesting thing is to show the difference with the lin space and log space, since last time there was a question about that. If we use log space, so I'm just going to make the same variable x, and I'm going to do np dot log space, and then I'm going to say -1, 1, 1, 1. Okay, so this goes from 10 to the -1 to 10 to the 1, so to 10, with 101 points. And I'm going to comment, so you can do, I think, Control-1 on your keyboard. In my keyboard, it's Command-1. You can comment and uncomment one line, which is very useful. So I'm going to comment this one. And since I'm using, well, let's see what that looks like. So if I make the same plot, you see that the distribution of the points is now not the same. Like there are more points at the beginning and fewer points at the end, right? Because if I do a log space from 10 to the -1, so 0.1, it starts somewhere here. So there are going to be a lot of points here. And then when you go to bigger numbers, they will be spaced out farther, which for some functions can be quite interesting, right? Especially for this is a quadratic function. So let's see what happens. So maybe I will make a second plot. Make a log plot. I'm going to do again plt.figure. So it's going to pop out a new figure. And then I do plt.log x, comma, y out, 1, for example. And I'm going to use this argument. Let's see what it does. and plt x label log x. So this is just the name of the axis, and plt y label will be log y. Okay, so we have this. Let's run this whole thing again. Okay, now I have two figures. This was our original figure, right? With a linear scale. Figure 2 is now a log-log plot. And of course, if you plot this quadratic function on a log-log scale, you get a straight line. And you see that if you zoom in on these points, that there is an even space between each data point on a log scale. So that's quite useful, right? So if we would keep the other spacing, let's go back to uncommenting the lin space and commenting the log space. If I run it like this, oops, sorry. If I run it like this, you see that on a linear scale, on a log-log plot, you will have very few points at the beginning, and then more and more and more points at the end. So it really depends on what function you're trying to plot and how. And so GS is green squares. So you can really play with the type of plot that you're making. Okay. Any questions about this very simple example? So clearly, you know, if I would do this myself, I would use the simplest possible method. So I wouldn't use a for loop with append, because actually this is slower. You don't notice it now because it's a very fast code anyway, but this is much slower than when you do a direct array calculation. So once you go to bigger models, the way you code things can really affect the time it takes to run it. Okay, so that was nice. Let's do a second example. So I'm going to copy my libraries because I'm going to reuse them. So I'm going to copy just this part. And I'm going to make a new file, file new. And so I have my new file, and I just copy my libraries back so I don't have to retype all that stuff every time. And we're going to work on a little example that is called the logistic map. And this is a very nice example. It's used a lot in population dynamics, and it's not a differential equation. It's called a difference equation, and we'll see how that works and what the difference is. But basically, a difference equation, you have a value x or whatever you want to call it, and you calculate the next value based on the previous value. So you can already think that you probably will need a for loop to calculate one point after the other. So I'm first going to define the function. And I'm going to call it def, so define, and I'm just going to call my function f to be short. And I have two input values. I have nt and r. And so nt, just write it here, nt is number of rabbits. Okay. And r is a constant. And that constant includes birth rate, death rate, and population pressure. Don't worry about all this stuff. Okay, so the logistic map is a model from population dynamics, and it's used to define, for example, animal populations, in this case, rabbits. Okay, so we can define my function. So I'm going to do return r times nt times 1 minus nt. So that's my function. So if I type the entire equation, let me write it here in the comments. Then I have nt plus 1. So the number of rabbits at time t plus 1 is the number of rabbits nt at the previous time times 1 minus the number of rabbits at time t times r. Okay, so nt, number of rabbits, nt plus 1 is number of rabbits at the next time point. Okay, I'm going to allocate some memory for my results. So I'm going to say res is an empty array. So this is allocating memory for results that I call res. And nt is 0.1. Okay, so number of rabbits, let's say normalized. Of course, you cannot have 0.1 rabbits, but let's say we have a certain density of rabbits and we start at 0.1. And so that's my initial condition. R is, let's say, 2 for the moment. And so that's my constant. Okay, so we're going to make a for loop. And we say for I in range of steps. Sorry, I forgot to define the number of steps here. So I'm going to say steps is 100. So that's the number of iterations of the for loop. So that means how many times am I going to run through my equation? If I do range steps, it will make an array from 0 to 100 integer. So 1, 2, 3, 4, 5, 6, 7, 8 until 100. Okay, so for I, so I call the first value in steps, which is 100. So 0, I call it I, and I put a colon, so it will run the next line. And I will say nt, so number of rabbits at time t is my function nt, comma r. Okay, so I calculate the number of rabbits at that time point, and then I say result.append nt. This is clear now. So I define the number of steps, 100. I go for the first value in that array from 0 to 100. I say that is I. In this case, I don't use I just use this to loop through this function. And so I said calculate the number of rabbits based on the previous one, nt, and append it, then go back, and it will just iterate this function 100 times. And then we can plot the results. So I can do plt dot figure, and oops, careful, plt.plot results. Okay, and I'm going to do plt x label. I'm going to call this generation, and plt y label, I'm going to call it rabbits. Okay, let's see if this runs. I press run, the green arrow here, boop, and I get something like this. So it starts at 0.1, it increases to 0.5, and then it just stays constant at 5. So what does this mean? When R is bigger than 1, the population grows to a certain size, and then it reaches a steady state. So it's constant. So what's funny about this logistic map is if you play with this number R. So for example, do the same thing, but change R to 3.3. Okay, let me just save this as test. I hit run, and now I get something weird, right? I start at 0.1, it increases, then something funny happens, then I get oscillations between different values. So congratulations, you made your first oscillating model. We'll get back to why that is surprising, but some of the properties, we'll get back to this, are very interesting. So this is a very simple equation, which gives you oscillations. And if you increase R even more, I don't know, 3.9 maybe, you get something that looks completely random. Okay. This in the field of nonlinear dynamics, which we're not going to go into huge detail, is called deterministic chaos. So you see a signal that looks, if you would be in the lab and you measure, some measurable quantity like pH or, temperature, and you would measure something like this, you would say, oh, it's random. So actually, we'll see later that this is not at all random, and that it can be understood. And what we have gone through is something called a bifurcation. So the logistic map is kind of the textbook example in nonlinear dynamics to understand the first oscillations. We won't go into that more now, so let's just keep it simple for the moment, because we first want to understand how Python works. Okay, so let's close this. And let's go to our first differential equation. Okay, so I'm going to, again, copy my libraries. Ctrl-C. I go to make a new script. And I copy them here. Boom. And we're going to need one more library now because we're going to go to a differential equation, right? So I'm going to import from SciPy. It's another library. Integrate. And from that one, I'm going to import. Oh, sorry, this is not import, but from. Sorry, so from scipy.integrate import ODE int. So I'm just going to pick one function from this library because it's a huge library. I don't need to import everything all the time. Okay, and we're going to solve an equation. And let me first do it on the board. Okay. Let me share this. Okay, so we're going to look at a very simple example. And we're going to say, let's imagine we have a reaction y goes to z with a rate k. Then we can, of course, write our rate equation, right? dy dt is minus k times y. Okay. Okay. Sorry, I should maybe just keep the same notation. Okay, so that's our rate equation. Let's do the analytical integration. Okay, this is now very simple for you guys. So we integrate from y0 to y of 1 over y dy, and that's minus the integral of 0 to t of k times dt. Okay, so ln y minus ln y0 is minus k times t, of course, minus k times 0, but this one falls off, right? So we have ln y is ln y0 minus k times t. So we have y is y0 times e minus kt. Okay, this one you of course already knew. So let's see, how are we going to code that up in Python? Okay, so we're back Python. And I'm just going to say here that I'm going to do dy dt is minus k times y, just as a comment. Okay, so I have my libraries, and I'm first going to define my rate constants. Well, constant, there's only one. So one thing I'm first going to do is I'm going to declare, as it's called, I'm going to declare my rate constant globally. So I'm going to say global k. That just means wherever I am in Python, I will have access to this value k that I'm going to define. And I'm going to say k equals 0.1. Okay. Now I'm going to give my function that returns dy over dt. So I'm going to say define a model, just going to call it model, with input y and time, colon, enter, and I'm going to call it dy dt equals minus k times y. So I just type my differential equation. I don't need to analytically integrate it, right? That's going to be the strength of Python, is we are going to numerically integrate it. So we're going to let the computer do the work. We just have to put in the differential equations, and Python takes care of the rest. Okay, and so I'm just going to say return dy dt. Okay, that's all I need to do. I need to give my initial condition, which is the concentration y0. Oops. Y0 is 1. So this would be my initial concentration of y, and this would be, of course, in molar units. Okay. So now I need to define my time points. And I'm going to use linspace. So t equals np dot linspace from 0 to 20, and I'm going to use 1000 points. And now I come to the most interesting part: solve the ODE, so the ordinary differential equation. So most of kinetics, right, unless you have reaction diffusion, so you have a space component. Let's say you want to solve chemical reaction diffusing in a two-dimensional or three-dimensional space, then you need partial differential equations. But 99% of what we will do will use ordinary differential equations. So they just have the normal d's that are italic, not the deltas, right? And I'm going to say the concentration of y at all the times is ODE int. So this is the ODE, ordinary differential equation, int integrator, right? So I'm going to integrate numerically my rate equation. So I'm going to say, what's the function? It already puts it here, right? So scipy dot integrate dot ODE int requires a function and an initial condition and a time. So we say the function is called model because I already defined it. My initial conditions are y0. That's the initial concentration. And my time is t. That's it. So what this will do for you is integrate your differential equation and calculate numerically the values of y. So let's go to plot results. All the same again. So I'm going to do plt.plot time on the x-axis, y, which is my integrated values for concentration. And I'm going to say label is ODE integrator. Okay, let's see what that looks like. We run it. Hey, I have a curve that starts at 1, of course, because our initial concentration is 1. And it seems to kind of decrease exponentially downwards. Okay? So that's kind of like what we expect. Okay. Let's compare that to the integrated form. So I'm going to say plt.plot. And I'm going to put the same time. And now I'm going to enter the manually integrated version that we made ourselves, right? Which was y0, y0, so the initial concentration, times np.exp, so that's numpy exponent, so that's just the exponent, minus k times t. And I'm going to give it a different style, so I'm going to say k minus minus, so dashed line, and label is integrated, so manually integrated. Let's add some labels. plt.x label time and plt y label is y as a function of t. Then we can also choose where we put the legend. That's also nice. plt.legend log, so location is upper right. Okay, let's run this whole thing. Invalid syntax. So I messed up somewhere here. So I'm missing a parenthesis here. Hop. Let me see. Run again. No. Line 36. I'm still messing up something. What?
You have an extra parenthesis at the end.
Oh, here. Yeah. Right. Okay, it's running. Okay, it ran. And so we see a nice plot with an X label, Y label. We have the values. And we see a blue line, which is ODE int, which is the numerical integrator. And we have a dashed line, which is our manual equation that we manually integrated. Maybe it would be interesting to increase the time a bit past 20 because it's still... yeah.
I'm sorry, Professor Hermans, you shared your window, not your screen, so I don't see the plot.
We don't see the plot. Desktop. Now?
Now we see it.
Okay, sorry about that. Sorry. Okay. Yeah. So we have the plot. Sorry, let me repeat. So ODA int, the blue one, is the numerically integrated curve, and the dashed line is integrated manually. So if you zoom in, you'll see that they are really, really, really on top. Okay, clearly, because that's nice. Let's increase the time a bit so we see if the reaction can finish. Right, it's an irreversible reaction. Let's maybe take 50. Run this again. And I don't have a plot because I should probably put plt.figure here. It told me just make a new plot. Okay, there we go. So if we look at time 50, more or less, the reaction is, you know, nearly 100% gone, right? I can read off the values of y here. So y, if you look at the bottom in the bar, it's 0.00101841. So almost everything converted. Okay, that is nice. Let's now, so this is the first order reaction, right? So I was telling you about half-lives and lifetimes. So let's add those as points in the plot. So I'm going to just here maybe insert in the middle.
Sorry to interrupt, but I just have a question before.
Yeah.
I don't really understand the point of return in line.
Yeah.
This line.
So return, so you can have all kind of calculations inside your model, but you can choose what the model gives back to your workspace. So in this model doesn't really seem to make sense, but you can have, let's say, more calculated calculations that you hide, and then you only give back to the workspace one function. So what let's say the function is of a function is you have just a name, you have an input, and you have an output. So return defines what is the output of your function.
Okay, I see that. Thank you.
So the question is why here we don't need plot figure. Okay, yeah. So that so typically when you make the first plot, it automatically makes it. But if you make multiple plots, then you need to define like PLT figure opens just a new window. So that's sometimes useful. If you just make one plot, it's not needed. But if you plot things over and over, it can be useful to open a new window. Okay. So back to the half-life. So I'm going to add my point, plt.plot. And I'm going to say, as you know, np, let's do first the yeah, the half-life. So np dot log 2, right? You know that that time, so the half-life is ln2 over k for first order, right? So I'm going to do np log 2 over k. And at that time, at the half-life, the y value is 0.5 times the initial concentration, right? That's the definition. So the half-life is the time to reach half the concentration. And I'm going to label that as the half-life. Okay. And the second thing I want to plot, plt.plot, is the lifetime, which is 1 over k, y0 times np exponent of 1. Okay, comma, O, and I label that lifetime. Okay, I'm going to run this. Okay, lifetime clearly is wrong. I don't know what I did here. 1 over k, y, oh, sorry, this should be y over np exponent 1. Right. Yay. Okay, so here you see half-life, right? So this is, I think, the most interesting quantity that we will work with is the half-life. This is where you reach 50% of the original, 50% conversion. So here we're at 0.5, and the time is, ln2 over k. So it's ln2 over 0.1 in this case, which is here. And here is the lifetime of the reaction. Okay, so we can, in this case, use the analytical solved versions for that to plot it in the figure. So that was basically simulating data, or numerically integrating differential equations. So that's very useful. Now let's do that again in a bit different way. But we're now going to try to fit some data. So this is a little bit more complicated, because basically what we will do is we will simulate or numerically integrate a differential equation, compare it to a set of data, and then the computer, the script, will iterate the value of k in this case to find a good fit with the data. So I'm going to delete this script. I'm going to keep my libraries, and let's use a bit more chemical notation. So I'm going to say the concentration of some variable that I call A. So I'm just, again, I'm keeping the same reaction. So it's reaction A goes to, let's say, P with rate constant K. Okay, so very similar, but I'm going to look at data we want to fit. Let's say it's experimental data. And I'm going to give it some data. So I'm going to call this t-span, time span is, and I'm going to make an array. So I'm going to say 0, 0.1, 0.2, 0.4, 0.8, and 1. I can throw that in the chat if you just want to copy paste it. There we go. It's maybe easier. And CA data, so that would be my concentrations of A that I've measured experimentally. 0.81, 1.5512, 1.19.3, 0.760, 0.2562. I'll put it in the chat in 1 second. 0.1495. Okay, so that's my concentration data. There we go. And I'm going to start by just plotting the data, right? We first want to just inspect if there's nothing weird going on. So I'm going to do plt.plot tspan, comma, concentration underscore data, round circles, standard blue, and plt y label is concentration of A, and plt x label would be time, whatever, t. Let's save this and run. Okay, so I run it. And I don't see the figure because it's somewhere behind. So I'm going to do plt.figure before. There we go. So we have a certain reaction. It starts around apparently 2 molar and it decreases over time. And it looks kind of exponential. So should be probably first order here. And that's nice. So that's looking at the data. And I'm going to make a new section where I'm going to say plot ODE with an estimate of K, so manual. Okay. So I'm going to set K to some random value. I'm going to say K equals 1.5. And I'm going to define my function, which is my ODE, right? So I'm going to say define, I'm going to call it my ODE. As an input, I have the concentration of A and time, colon, return minus K times CA. So here, with respect to the previous code, in the previous code, I first made something that I called, dy dt equals minus K times CA. Here I'm just a bit shorter. So I'm directly putting just return minus K times CA directly there. Okay. Okay, so I'm going to make a variable that I call ctemporary, ctemp, so temporary concentration. And I'm going to use ODE integrator. So I'm going to integrate my model, right? So my function is my ODE. My initial concentration is CA data 0. So the first experimental data point that we put, right? That's my initial condition. And I'm going to do NP linspace 0 to 1 because my time is going from 0 to 1, right? But I'm going to put 100 values. Okay. And let's plot that as well. So I'm going to add that to the same plot. I'm going to do plt.plot np dot
Excuse me? It's not MP?
All right. Yeah. Right. NP, of course. Sorry. Typos are always dangerous, but it happens. Okay. NP linspace 0,1 100. Right. And I'm going to plot my temporary concentration data, and my label, I'm going to call it manual, because it's just an estimation, right? I'm fixing my value K at some whatever value I estimate, and I'm going to make this integration over starting from my experimental data point, going from 0 to 1 at 100 points, and I'm going to plot it. So let's see what that does. Oh, that's interesting because I forgot here. Bracket. And there we go. So I have my data points, experimental, and I have my line here, which has a K value, which is not right because clearly this is not fitting well to my data. But I could maybe say, okay, maybe if I do 1.6, it's a bit better, 1.7 maybe. Okay, I'm getting closer, 1.8. Right, so this is not fitting, right? This is still, you're just overlaying your model with your data. But it's good to start like that, because if you start a fitting routine and your initial guess of K is super far off, let's say you say, oh, okay, it must be 10 to the 9th or something, then your solver might not find actually the right solution. So I always like just by hand to go and get it more or less in the right neighborhood. So, okay, probably it's bigger than 2, maybe 2.1 or something. I don't know the actual value. Okay. But okay, we're pretty close. Okay, it's not perfect, but we're pretty close. So I know that K is more or less in the range of like 2.1, something like that.
2.6 is really good.
2.6. Okay, let's see. 2.6. Oh yeah, that's pretty good. Okay, so 2.6 is probably a good guess. But now if I ask you, give me the number with 8 digits behind the comma, you're going to spend a lot of time by hand to try to fit this. But in any case, it's good to manually play around and get more or less good value. But this, you cannot report this in a paper as I manually fit a model to my data. No one will accept that. But it's good to know more or less the manual number. So we have, this is a good idea. So let's say good initial guess of K2 of K. Okay, so nice. So now we're going to make a new function, which we're going to call fit function. Okay, this looks a bit complicated. I'm going to make a little break here. Okay, so I'm going to say define fit function. So maybe it's useful to explain first how a computer fits data. Anyone has an idea of how that works? Let me just bring up my board. Okay, 1 second. Yes, there we go. Okay, so I have my data. Oops. Okay, I have my data points. And I have my model, which initially was not very good. what does a computer do? What does a fit function actually do? So it will calculate the sum of the errors squared. What does that mean? So it looks, okay, here I have the same initial value, right? So let's say my model value is this. I take minus my real value, and that is my error. And the reason why they take the square is this number can of course be negative or positive, but if you square it, then it's always positive, right? So I do that for each point. So I look here, okay, I have a certain error, and here I have a certain error, and here I have a big error. So what the computer does is it takes the sum of errors squared, and it tries to minimize that. Okay, so it will change the value of k. That's kind of the logic it does. So it says calculate the errors, change k, calculate error again, and then it actually knows in which direction it should change, and it tries to find the lowest value. And typically this is a pretty simple problem, so the solver will have absolutely no problem to find, you know, the correct minimum of errors. But sometimes you can kind of think of it as a landscape. So let's say if I start here and my lowest sum is somewhere here, then this is easy to find. You probably heard about Euler's theorem or something like that. So there are different ways to do that. So in most of the solvers nowadays, they have adaptive solvers. So they will switch their algorithm based on your solution, and it's all automatic and you don't have to worry about it. Okay, that's basically what it's going to do. Sorry, let me share again my desktop. There we go. So I'm going to define a fit function that has as an input time and my k value. And so I'm going to just put a component here. So this is the function that returns CA computed from the ODE. And okay, so here basically I can reuse the same one. I'm just, for simplicity, I'm going to type it again, my ODE CAT. This is redundant, but just for clarity, if later we are going to remove this manual part, let's say manual part, oops, k, return minus k times CA. So this is all still the same. And okay, I'm going to say CA0 is CA data 0. So this is the same. So this is my first initial concentration of A. And CA solution, I'm going to call it. So that's my solved concentration. Again, the same, ODE int, my ODE CA 0, comma T. Return CA sol. And I'm going to return the first Okay, all the rows, the last column. Okay. So let's go to the curve fitting. Okay, so I'm going to use a curve fitting function that's called curve fit, and it gives two outputs. It gives, I'm going to call the first one k fit. So it's the fitted value of k, and k covariance. So it's going to give the covariance of k. For the moment, let's not care about that one. And so I'm going to call this function curve underscore fit, which I take my fit function, okay, time span, CA data, and my initial guess for k, I guess I can call it k0. And I will put, let's put 2.6 because that was already pretty good. Okay, so this function takes my fit function that has as an input time and k, then using the same function as here. So I'm going to comment this whole part, okay? So this is now turned off. I just selected the whole thing and then I do control 1 or command 1. So that part of the function is now skipped. So I again calculate my initial concentration. I have my model, which is this one, right? Which is just giving you the concentration integrated numerically, my initial concentration, time, and I return my solved solution out. And now I'm doing the curve fitting with using that function, this time, this data, and initial k. I'm not sure if this will work, but let's see what it does. And then I'm going to say generate many data points using the fitted value of k fit. So I'm going to, so the solver, this will just give me a value of k fit. And so I want to plot those fitted values again on top of my data. So I have to, again, generate lin space. So I'm going to say tfit. So that's my fitted time is np.linspace 0,1. And fitted values is fit function, where I put in tfit and kfit. So this will give me the concentrations using the fitted value kfit and this time, which is just a lin space from 0 to 1, because my t-span is also going from 0 to 1. So I'm just putting more data points. By default, it's 50. So this will generate 50 data points. Okay, so we go again to plot it, plt.plot. Sorry. T-span. Well, actually, we're still plotting here the data, so I can skip that part. And I'm just going to plot my new function. So I'm going to say plt.plot tfit fit. I will make this a line and I will call it fit. Okay, maybe I can add here also label just to make it extra clear. Label is data. Okay, let's see if this runs. Curve fit is not defined. Okay, yeah, so that means we probably forgot to import something. Yes, we did. So curve fit is part of another library. So from scipy dot optimize import curve underscore fit. Okay, so this, I forgot to add this line, which then it doesn't know what curve fit is. Okay, so now it does. Let's run it again. Unexpected arguments on line 48. Yes, so I was just trying this out. So apparently in curve fit, your initial, let's see what it says. P0 is the initial guess. So apparently we have to use P0, it cannot be K0. Okay, my mistake. So P0 here, that's the initial guess for whatever I'm trying to fit. And that is going to result in K fit. Okay, let me run this. There we go. So now we have a pretty cool blue line, which is going exactly through my data points. And now I'm interested to see K fit. So yeah, 2.6 was a pretty good guess. But in reality, it's 2.5889346 with a covariance of 5.35, 10 to the minus 5. So it's a pretty good, fit. Sorry, maybe I will reset 1 second because all the old values are still here. So let's just quickly rerun. It's a bit cleaner. So those are my variables, right? CA data is my manually inputted data. K-fit is my value with K-cof. And actually, so fit is my fitted concentration data with the time span, okay? So that's, well, the easiest way to fit an ODE to data. So this is, okay, your first encounter maybe with data fitting, but you see what the power of Spider is that I don't have to analytically integrate anything. I just throw in my differential equation here and it numerically solves it and I can fit it to data. And this works also if you have a couple differential equations, maybe you have a sequential reaction that you want to solve. We'll see in the next class much more complicated networks of reactions that analytically by hand you will not be able to solve them anymore. But numerically we can solve incredibly complicated networks of reactions, which will be fun, I hope.